So today we will discuss uh, concepts like entanglement, separability, and entanglement. So before that, I want to state a result from linear algebra. This is what is called, you might be knowing it, singular value decomposition. You know this? Any matrix X from M or any linear operator, any matrix is fine, Mn cross M C, okay, which is a linear operator from Cn, C M to Cn, okay, Cn. Okay. Then with the dimension of the range, which is the rank of X equal to R. Okay. Then there exists ortho, not basis, ortho normal vectors, say Ek, k equal to 1 to R, okay, where R will be less than or equal to minimum of, R has to be less than, okay, let's say, I better call it as HA and HB, which is like notation so that it will be useful here. X is in L of H A to HB, HD to HB. This is with dimension dA, this is with dimension D. Okay. And this will be less than dA, dB. Of course, always rank is less than dA and dB. And k equal to 1 to n. So this is in the, I think this should be in HB. It's from HA, and FK. Again, the same k equal to 1 to R in HB, such that X is equal to summation, and there exists, and I mean, if you are given any X, this is like a spectral theorem. I mean, it's not spectral theorem. It's not a special case of spectral theorem or something. It's like something like that. You have something, some sort of diagonalization. So you have a X, arbitrary X, operator from HA to HB, whose rank is R. Then there exists orthonormal vectors in HA, in HB, which are indexed up to R vector, R such vectors. And you have some SK strictly greater than 0. Okay, where k equal to, of course, k equal to 1 to R. Okay, there are R such positive numbers such that X is equal to summation k equal to 1 to R, okay, with Sk times. So which one should come here? I mean, this should land up here, so it should be Fk Ek, which is right. I mean, this is right, no, right? I have written it correctly. Ek, Fk Ek. Okay? It will take a vector from there and hit it with Ek and leave it. Okay? So it's not like, I mean, it's not like it may be different spaces also. Okay? So this is, I will not write a proof of that, but I can give you a proof. You know, polar decomposition. No? From that we can give a proof. So what usually happens, what the idea is the following. This will follow if from this. X will look like, I mean, the usual singular value decomposition in any textbook, linear algebra textbook is this. U sigma B, maybe V transpose, like you can write V, okay? Where you, I mean, any X will look like this if there exists unitaries. U and V, okay? Unitary in, this will be in L of HA, this will be in L of HB. It has to, it's here, so it should be that. And sigma is a diagonal matrix. Diagonal with, I mean, it's a rectangular matrix, it's not a square matrix, but it has R diagonal elements which are positive, with R diagonal elements strictly greater than 0. That is something like this, is S1 up to SR, okay? and 0 everywhere else. So it is equal, this is equal to this. I mean, any unitary, if you take the usual orthonormal basis, the indexed by this I or whatever, it will take this to some orthonormal basis. I mean, which will be the column of this unitary matrix. Then you apply this. Okay, on that, I mean, it will take usual orthonormal basis to some orthonormal basis. Say that EK, say EI, yeah, it will take it to. It will take it to what? It will finally, just will take it to EK, and there it will act as this SK, and those orthonormal bases will be again taken to some other orthonormal basis, FK. So that is what unitary is. I mean, any unitary takes the standard orthonormal basis to the column vectors of this unitary. Okay. So this is equivalent to that. Okay. And you can find that this V is, I mean, which has columns with see, if you have X, then X transpose X is a positive matrix. So they have eigenvectors. Spectral theorem is applicable to that. So it's columns with eigenvectors of X transpose X. I mean, I'm just telling you the result, but you can prove it using linear algebra. We will prove it using polar decomposition. I assume polar decomposition. Maybe I will sketch the proof orally, okay? Which you know you have seen here. Okay, so and X transpose X. I mean, V is just the V has columns which are the column vectors or eigenvectors of X transpose X, and U column with eigenvectors of XX transpose. Both will have the same eigenvalues. I mean, X transpose and X transpose both will have the same eigenvalue, okay, which you can follow from linear algebra. Okay, and then this Sk is equal to square root of lambda k, where lambda k are eigenvalues of this one. Okay. Lambda k positive eigenvalues. Values of this X transpose X. Okay, if you substitute that, you will get that. So this is one way of saying that. So if you take polar decomposition, any X can be written as U, a partial isometry times. Sorry, I wrote. I mean, it should be star, not transpose. It should be. I mean, when we write here, it will be star for us. Right? It's a transpose for real. Okay. So you take X star X. This is positive, so you take the power. This is how the polar decomposition will look like. Any X will look like U times this. But I mean, this is general for any Hilbert space, infinite dimensional or something. Any operator, linear operator, can be written as a partial isometry times this. Where these are unique up to some kernel condition. The kernel of X should be equal to kernel of U kind of thing. I mean, so there are some conditions. If you drop that condition, and when the rank of kernel of X is same as kernel of rank of kernel, dimension of kernel of X and dimension of kernel of X star, they are same in infinite dimension also, then you can replace this U by a unitary. Okay. How is this polar decomposition defined? You take any vector, you take this Tx. Okay. This will be range of Tx, of course. The range of mod Tx. Mod T is this. I am saying T, sorry. Mod X equal to take X star X power half. Okay. So range of mod X is same as range of X star X. Same as range of X star. Okay, I mean maybe the kernel perp you can work with that. Okay, then I mean kernel perp of all these things are same. So on this range of mod X, you define this operator X xi going to X xi. You can check that this is a unitary operator on this range X to whatever Xi. I mean, that will be kernel perp of X star. Okay. So, and you have defined the map on these ranges. This is kernel perp of X star. That is kernel perp of X, right? Whatever. I mean, it is just you have a partial asymmetry between them. Between the kernel, you don't have anything. So, but when the dimensions are same, you can take some unitary between them. So you can replace it with the unitary when you have. So in finite dimensional, it is the case. Rank of x is equal to rank of x is not. So any x will look like that with with u unitary. I mean, you can write it like that. This is not unique because on the kernel you can have different things, okay, with u unitary. Okay. So any x will look like this. This is a positive matrix times u. Okay. Now it's clear, right? Now you take the eigenvalues of x star x power half. Okay. You call that sk. Okay. That will, I mean, you take this, you assume the spectral theorem. If you have the eigenvalues of this, eigenvectors of this, call that ek. Okay. It will act as some sk times on that ek. Then you will transform to some other eigen. So this is clear. Okay. So take ek to be eigenvectors of x transpose x or x transpose x, both are same, both have same eigenvector. X transpose, they are, it's just the square root. Okay. So both have the same eigenvectors. And fk equal to u of ek. That's all. And sk equal to just eigenvalues. Eigenvalues of this x transpose x power half. So now this will work. Okay. So any x can be written like that. Okay. This have the following consequence, okay, which is called Smith decomposition. If you have two vector space HA, HB, then you take HA, H tensor HB equal to call it as HAB. You take HA tensor HB, we have two Hilbert spaces. Then we have a vector in this HAB. Okay. Then there exists lambda k positive with, so this chi will give you a matrix, right, with R is equal to rank of x, where where x tensor 1 of gamma equal to vector of, I mean, where we already know what is, I mean, we already discussed this, but what I want to say is where the vector of x is equal to that. Okay. This is in one-to-one correspondence with L of HA to HB and L of HB to HA, whatever, HB to HA, right? Yeah. So it is that. Okay. So now you have when you have something chi, you can associate a matrix to that. That matrix has rank R. Okay. Then you have lambda k equal to 1 to R. And Ek k equal to 1 to R. The vectors contained in H A and Fk k equal to 1 to R contained in HB, such that this chi is equal to summation. We have I take square root of lambda k, k for some reason. I mean, because we want to use, when we use square root, because we usually want to consider the state. The state will be chi, right? So there we want to get lambda k. So that's all. Okay. So this is the SK. K equal to 1 to R, Ek tensor Fk. This is direct from the previous, right? You have x. X can be written like this. No, there is no mod. If lambda k is the eigenvalue of x transpose x star x, okay, then its square root is sk. This is just the eigenvalue of x star. I am writing transpose everywhere. I don't know why. It is just star. Okay, there is no x star x power half. It is just the eigenvalue of that. Okay, you have the unitary v. You have the unitary v acting on that. Then this is the eigenvalues of x star x. It's just the mod of x, which is called x star x power half. And so I'm taking square root because here I'm stating it as the eigenvalues of x star x. Because that is the eigen. I mean, you can take the eigenvectors of x star x and x star x power half, both are same. See? So you can take anything you want. Okay. So any x can be decomposed like that, like this. Okay. Now this will go to ek tensor fk there, right? It will go to ek tensor f. Okay. Yk is sk. Sorry, this is sk. I have written ks for some reason. Okay. So yeah, this will go to ek tensor fk, and that's what we want. Okay. So this is clear. I don't have to prove it, right? So it follows from singular value decomposition. Proof follows from the singular value decomposition is usually written as SVD. Yes, follows from singular value decomposition. So this is clear. I don't have to prove it. Okay. Okay. Now we will define entanglement and separability. Okay. Of course, it is for tensor product. A vector chi in HA tensor HB is no, it's for mixed state. Sorry, I want to define for mixed state. It's a general definition. Let rho in L of HA tensor HB is a state. Okay, it's a state on HA tensor HB. That means it's a positive operator and with trace 1. Okay? That is rho greater than or equal to 0 and trace rho equal to 1. That's all. That's the definition of a state. Okay? Is said to be separable if there exists P1 to Pk, yeah, that's okay, Pk. Okay, maybe Pk I'm using, so P1 up to Pd, okay, Pd. But okay, I will use K. K, P1 up to Pi, I equal to 1 to K. Pi, I equal to 1 to K. Okay, these are numbers where Pi is less than or equal to 1, greater than or equal to 0, with such probability measure. Summation Pi equal to 1, P equal to 1 to K. Okay. There exist K numbers between 0 and 1. This is like a finite probability distribution. Okay, so that we take convex linear combination and omega I, omega ai, and omega ai, I equal to 1 to K, okay, and omega bi with I equal to 1 to K states on HA and HB respectively, okay, such that this our rho is equal to summation Pi omega A is on the top, yeah, I tensor omega bi, okay, Pi, I equal to 1 to 3. This is what is called a product state. I mean, a state need not be written like that. It will be usually linear combination of that. This is a convex linear combination of product state. That is what we call as separable state. A state is separable if it is convex linear combination of this product state. Okay, I will not define. Okay, maybe I will define. Yes, maybe I will define here. Okay, rho is a product state if rho is equal to some omega A tensor omega B. You can factor it like that in the tensor product. That is called a product state. If it is convex combination, okay, it's like a probability measure. You have some probability, finite probability measure. Convex combination of this kind of product state, then it is called a separable state. Okay, this holds for any pure state also, the same definition. Okay. Now you know a state is a positive operator. So any state, I mean any state omega A on anything is equal to summation some lambda I times ei, right? It's just the spectral measure. Okay, and so if this any of this omega ai, I mean this rho is equal to summation pi into omega ai tensor omega bm. So omega ai will look like that for some lambda in something. Omega bi will look like this. So and you have a pi, okay. So you can write the product and everything. Finally, what will happen is rho will look like some new pi, okay, new pi prime, okay, where I ranges from something to something, okay, such that this will look like this. This is ei tensor fi. All I'm saying is, if it is convex linear combination of product state, it is convex linear combination of pure product states. These are pure states. Okay? This is a convex linear combination. You can by decomposing this as product, any state is a linear combination of pure state. Pure means this kind of states are pure state. So anything is a product linear combination of pure state. This is another linear combination. Summation lambda I should be equal to 1, right? Summation lambda equal to 1 and lambda I is greater than or equal to 1, right? Because it's a state. The trace has to be equal to 1. So because of that is true. So when you take out the lambda I, everything, that will again be a probability distribution like that. You can verify it. Okay, so it's algebra verification. Okay, so because of that, any row can be written like this. So you can decompose as product state, which are pure states. Okay. 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 Now proposition. If okay. I mean pure state on HA tensor HB. If you have a pure state, which will look like that, of course, for some chi, okay, for a chi in this vector, if a pure state is separable, then it is a product state, if and only if it is a product state. For pure state, for mixed state, you have to have the convex linear combination. Okay, but if you have a pure state, the original state rho, which you want to define it as either separable or entangled, if that is a pure state, then it is a separable state, if and only if it is a product pure state. I mean, it's a product state, product of two pure states. Because anything is just a convex linear combination of pure state, and that linear combination has to be exactly that is only one. That's what it says. Okay? So proof is clear. So wait, suppose let chi equal to summation pi times ei tensor fi okay, I equal to 1 to k, whatever. Now you take inner product with this. Okay, Now you take this is equal to rho. Rho. Now you take rho with chi itself. Okay. Equal to 1, of course. I mean, it is just you take inner product with chi and then inner product with chi there. That will be 1. Okay. That will be 1 square, which is 1. Okay. Chi is 1. I mean, this is a unit vector. It's a state, means in a pure state, it should be unit vector because of its 1. So 1 is equal to, here you get summation I equal to 1 to k, pi. I take I take chi and the inner product with this, right? Ei tensor fi. See, if I take inner product with chi here, I get, I mean, chi here, I get these two. This is just Ei tensor fi, pure state with Ei tensor fi. You can remove this tensor, put the tensor in the middle if you want. Okay. So it will be have the inner product with chi Ei tensor fi and Ei tensor fi chi, which is just the, then you have the product of these two things, which is square of this. Right? You have chi here. Okay. And you have chi here. I mean, chi. Okay, I will write it. This is equal to 1 is equal to, this side is 1, of course. If you take inner product with chi, this side is 1. And this side you get summation pi. Okay. This is same as this, right? Chi ei in a tensor fi. I mean, this is equal to ei tensor fi. I mean, you take this as one single vector. Okay. And it is with respect to ei tensor. The same thing, right? You can write this tensor, you can put this tensor ei tensor fi, ei tensor fi. It's the same thing, right? I'm just saying that as matrix ei tensor fi, tensor fi fi is same thing as you take this vector ei tensor fi, which is a vector. Okay. And then you take ei tensor fi. Okay. Sorry, this way. It is that way. Correct, no? So yeah, this way, correct. It's the same thing, I'm just saying. Okay. You can take it the individual tensor, which, okay. Because of that, this is just going to be, you just chi ei tensor fi, and then you have chi ei tensor fi, but it is just a conjugate. Because of that, you get the square of this. Okay. Square of this. Okay. Okay. K equal, I equal to 1 to k. Okay. Now summation pi equal to 1. Okay. Summation pi equal to 1. Now this should also be 1, means this has to be 1, right? This is less than 1, of course. By Cauchy, this is of norm 1, this is of norm 1. So the inner product will have, I mean, square will have less than or equal to 1. But if summation pi has to be 1, it shouldn't get reduced. This has to be equal to 1, right? So this, because summation of pi equal to 1, this implies that chi ei tensor fi, this inner product should be equal to 1. Okay? It should be equal to 1. But then this is a unit vector, this is a unit vector. The inner product is 1. I mean, Cauchy-Schwarz says that this is less than or equal to 1. Cauchy-Schwarz says that this is less than or equal to norm of chi times norm of ei tensor fi. That's what Cauchy-Schwarz says. In Cauchy-Schwarz, equality holds if and only if one is a constant multiple of the other. Equality holds. So here equality is hold. So this is equal to 1. So here equality holds. When the equality holds, they have to be scalar multiple of the other. Okay? But since they are state, that scalar has to be positive. But it has to be 1 only. It cannot be other scalar because then the norm will change. So they should be equal. So this implies chi is equal to ei tensor fi for all I. For all I. So you can take the summation Pi equal to 1 and this is equal to, there is only 1. For all I, this is equal. This is just here. So any separable, any pure state is separable if and only if it's a product state. Converse is clear. Anything is converse is clear. Pi, there is only one P, so it's fine. Okay. So this is like orthonormal. I mean, any EI, I mean, it just says that chi is equal to E, one single E tensor, one single F. Okay. This means that the Schmidt rank of this is 1. Okay. So we from that we get that, I mean, whatever Schmidt rank is, the number of elements in the Schmidt decomposition are. Okay. So corollary, a chi, a pure vector chi in HA tensor HB. So we alternatively call a vector as a state, or I mean, it's a unit vector as for pure state, either a vector as state, or you can take the chi, whatever. Okay. So HA is separable if and only if the Schmidt rank is rank is 1. Okay. So definition, a state rho in L of HA tensor HB is entangled if it's not separable. Okay. Any state which is not separable is entangled. So yes, pure state is entangled if and only if its Schmidt rank is strictly greater than 1. Okay, that's what it says. Okay. Now example. Just you can take C2. Yeah. C2 is C tensor C, right? No, not C. C2 tensor C2. I mean, to get it something non-trivial, we need at least 2 dimensions. If it is 1 dimension, then there is, I mean, C tensor C is C again. So it's C2 tensor C2. Okay. So in C2 tensor C2, you can take, so the vectors here are 0 and 1. Okay. And here the vectors are 0 and 1. Okay. You can put it together. Then this vector 0, 0, okay, plus 1, 1, which is just 0 tensor 0, 1 tensor 1. Okay. 1 by square root 3 to make it unit vector. This is an entangled vector. And you can put a minus sign here. That will also be an entangled vector. And second thing is 1 by root 2 and 0, 1, 1, 0. Okay. This is also an entangled vector. Okay. It just flips the 1 and 0. Okay. And you can put a minus sign. This is also an entangled vector. All these 4 vectors are orthogonal to each other. C2 tensor C2 is 4-dimensional. So you have got 4 vectors which are entangled and they form an orthogonal basis for C2 tensor C. Okay. But this is what these are what is called, what is it called, EPR pair, EPR orthogonal vectors. Okay. I mean, this comes from Pauli matrices, which we discussed already. Okay. How we get it? Because if you have, I mean, I will come to that. Okay. So this is another definition. Let dA equal to dimension of HA. Okay. Then a chi in HA tensor HA is maximally entangled if the Schmidt rank is rank of chi is D with those values, no, Smith eigenvalues or whatever, did I call anything singular values or something, with those values 1 by square root D. Square root D. I mean, those singular values. There are some S1 up to SK, SR or something. So those things are all Smith value with the, what did I call? Did I say anything? Those singular values. Okay, I just call it Smith. Maybe I'll change it later. I don't remember. With singular values. For a general matrix, those lambda 1, I mean, whatever the S1 up to SR, they are called singular values. So here let us call it Smith singular values. Okay. Values all equal to 1 by square root D. This is what is called a maximal entanglement. Okay. And these are all maximal entangled vectors. I mean, they have this, there are two of them. So it is this. The rank is 2, and the singular values are 1 by root 2. So they are maximally entangled. We have already seen 1 by square root of D gamma, where this is 1 by square root of D I tensor I. Summation I equal to 0 to dA minus 1. We have already seen this, right? So this is, there are dA vectors, dA number of vectors, and each has singular value 1 by square root D. So it is a maximally entangled vector. So this is proposition. I just a remark. Okay. This is clear. Remark. Yes. If you have a vector chi, okay, let's prove it for this. It's generally also true. So let us just notice that you take this gamma 1 by square root D, which is an HA tensor HB, HA tensor HA. Yeah, HA tensor HA. Okay. So this is a state. Okay. This is a state. You can consider it as the product state as a matrix also. Okay. Then the trace, partial trace of A of this. So if you take 1 by D, that will be 1 by D. This is a pure state. Okay. If you take the partial trace of this, you can, this is equal to what? Trace A of 1 by D into summation EI tensor EI, right? I mean, EI tensor EI summation EI, EJ. I mean, this will be EI tensor EI, this will be EJ tensor EJ. So it will be EI, EJ, right? Right? Tensor EI, EJ, right? This is what we get, right? This is summation EI tensor EI. This is summation some EJ tensor EJ. So if you take the product like this is what you will get. Okay? Now you apply trace EI. Trace EI is just applying trace here. This is only when j equal to I, it is 1, otherwise it's just 0. Okay? So this will be equal to 1 by d into, this will be either 0 or 1. It is 1 when j equal to I. So this is just summation of EI, EI. It's just identity, right? I have written EI. I mean, I should have written this I, sorry. This I, same as EI, okay? We write EI or this I or whatever. Okay? This is equal to I equal to 1. This is 1 by d, which is just identity, right? This is just when you have all orthonormal vectors. I mean, whole orthonormal basis is something like that. This is just identity. 1 of HA by D. This is a matrix, not a product, pure product. I mean, this is a identity. I mean, this has n sum of pure state, n vector, sum of n pure state. Okay, so it's a highly non-pure state. But we started with the pure state. When we took the trace, we get this. This is the quantum phenomena. I mean, it's like you start with something, a pure state, you take the partial trace, which is like taking conditional expectation or marginal. Marginal. In this state, it's marginal because that is state. I mean, state is like a probability distribution. So it is like taking the marginal. The marginals are not pure. So this can happen only in the this quantum setup. It's not in classical probability. It's not true. If you have a pure state corresponding to delta measures. So if you take delta measures, it will give delta measures as marginal. Okay? Here it will not happen. Okay? So similarly, trace B of the same 1 by d gamma. Okay, whatever. I want to write, I mean, you want to, maybe I write it. Gamma is also again, if you take it, you have to take it here. One tensor trace, you have to take the trace here, the second component, it will give the same. That is also 1 HA times by D. Okay. Now let U1, U2 or L of HA unitaries. Okay. I want to say that U1 tensor U2 acting on gamma by 1 by d is also maximally entangled. It's clear, no? This will have EI tensor EI. U1 will act on that and get to a orthonormal basis. U2 will act on that, get to another orthonormal basis. So this will just look like 1 by d EI tensor some Fi. I mean, this EI is not that EI. This is, if you want, UI, okay, UI, okay, U1I tensor U2I. Okay. This is how it will look like. And this is also a Smith decomposition with orthogonal basis. There are D of them. There are D of them, and each one having the Smith eigenvalue, Smith singular value 1 by D. So this is also maximally entangled. So if you take any U1, U2, you get maximally entangled. And here also, if you take trace of any U1 tensor U2 of gamma by D, okay, see the same thing will work. You take you just have here U and U1 and U2. You have U1 and U2 here, U1 and U2 here, right? No, in the first component it is U. The second component, this is EI tensor EI, so it will be U1, 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 U2, U2. That's what you will get. Okay, and there also it will have the trace. It will be. I mean, see, you take any UE, any U, E or F, whatever. Okay, this is nothing but U of E, F, U star. Okay, and the trace of this, you can take the U there is equal to that. Okay, so if you insert a U there in this sum, for example, the trace is going to be either only when I where we compute I equal to j. If you even if you have a U here, the trace is equal to 1 when I equal to j, otherwise it's 0. So you will get the same result. You will get instead U of something, but that will also sum to 1 only. So if you have these kind of maximally entangled state, here also if you take the trace with respect to A or B, you are going to get identity 1. Right. Okay. If you take the partial trace, this is what you get. This is clear? Okay. So this is what you will get for any of these kind of things. But what we have seen from this is, if you take this vector, this is a fixed maximally entangled set. It's like an identity. Then by applying U1, U2, you get many entangled, maximally entangled states. And that is what you are doing here in this example. In this example, EPR, this is called EPR thing. I mean, this is called EPR, Einstein, Podolsky, Rosen, because they got that you must popular article, you must have heard spooky action from a distance, all these things. No? I mean, it is like, see, they want to say, see, when we come to measurement, I will tell you. When you measure, you have heard, know this, have you heard these things? I mean, the Einstein's paradox, EPR paradox. In EPR is Einstein, Podolsky, Rosen. These are the 3 people. They want to somehow contradict quantum mechanics. Quantum mechanics as a contradiction, that's what they want to prove, which is solved by Bell later. Bell in 65, 60s or something, which is proven, I mean, mathematically it was solved, which is proven last year or something. And this guy, it starts in A, French guy, Aspect, Alan Aspect, got Nobel Prize, no? That's because he proved it experimentally, Bell's theorem. Okay? So that's because of, I think I'm saying correctly. So he got it Nobel Prize last year or the year before, I don't remember. Okay? So that is for experimentally verifying the Bell's inequality. Okay? This is called non-locality or something. So, I mean, the thing is, information cannot travel faster than light. That's what Einstein's theory says. Okay? Quantum mechanics, whatever they have developed, all these other people, non-Einstein people, Einstein is not part of it. Einstein was against quantum mechanics. Okay? He's a genius. He created all that, but then he wanted to disprove quantum mechanics throughout his life, which he didn't succeed. And quantum mechanics has been a successful theory. Okay? I mean, unfortunately, Einstein is not correct, but it's still not clear. Okay, but it's successful means explaining everything. But there is a problem of relativity, and the relativity was large object. Quantum mechanics is for small object. These two are not compatible for some reason. There is no one theory which connects these two theories into put it into one single theory. There is no such thing. Physics is incomplete in that respect. Okay, so Einstein, using these states, he got a counterexample, because when you measure this, suppose if you have two two electron with spin one in positive direction, you call it 0. Spin in other direction with the 1. We have two electrons, which I mean by 0 means it's spin in one direction, 1 means spin in the other direction. Suppose they both have this state, which is called entangled state. Okay, so you have one electron here, you have one other electron anywhere in Andromeda galaxy, which is 1 million light years away. Okay, and you measure this electron here, what is happened? Suppose if it has 0, the other one should have 1 or something. I mean, the measurement is something collapse of the wave particle. So if you measure it, it will not have any more have this quantum property. It will not be in both the states 0 and 1. There is no superposition. It will collapse to one single position, 0 or 1. So when this collapses, that should also collapse. Okay, but then this collapse here, this information cannot reach before million years because light will travel that much time to reach there. See, it's like if you remove the sun, something, Earth will still be orbiting the sun, even if sun is not there for 8 more minutes, because the information can reach only the sun is not there. That information will take 8 minutes for Earth to reach the Earth, even for the Earth, which is a non-living object. Okay, so after that only Earth will start tangentially start moving into the space. Okay, so like that, if you measure an electron, the other electron will know that this is measured. So we have to collapse to that. It will know that, it will know I have to collapse. I mean, it will collapse. Once the measurement is done, it will collapse. It will know 1 million years later because it is at 1 million light years away. But according to this, it will collapse immediately. So quantum mechanics is, but that's Bell inequality. We will see. We will try to, if we have time, we will see that. Okay. So for that, these states are used. Okay, it is this state. So that is why it's called EPR state. There's no other reason. Mathematically, it's such a simple thing. Okay? It is just a vector written like that. Okay. Okay. So what we have is, if you have one maximally entangled state, E8 tensor EI, summation E8 tensor EI, then by applying all these unitaries, we get as many entangled states as we want, not as many maximally entangled, so that we can have orthogonal basis and all that. Okay. So what is next? Okay, there is a generalization of this polymatrices. So maybe if you remember, I was talking about Fock space and something called Weil operators, but there is a finite, that is much more generalization, infinite dimensional generalization. For a finite dimensional generalization of this polymatrices is as follows. Okay? This will, I will leave it as an assignment. All the properties, it's very easy. Just you have to verify the definition, using the definition. By the way, you submit the assignment by the end of this month, February. Okay, whatever I have done. Okay. So let our HA is a d-dimensional one, CD, call it CD. Okay, and of course with ONB 0, 1 to D minus 1. Okay. D minus 1. So we have orthonormal basis like that. Then you define U K, whatever, K acting on any I is equal to, this is just diagonal action. Okay, e power 2 pi I. This I is square root of minus 1, imaginary I, not the index I. Okay, times this K is sorry. That is, so here we have I. That's the problem. I have to use K. Sorry, K prime. I'm sorry. Sorry. If I use I is square root of minus 1. Okay? So I cannot use K prime. UK acting on K prime vector is just K prime. You have to divide it by the dimension D times K prime itself. It is just the diagonal action. Okay? Diagonal action. But you will have the scalar will depend on this K prime and then this. There are different diagonals. is clearly unitary. These are all of modulus 1. So this is clearly unitary. Okay. And another Vk acting on K prime. I think it's okay, what I have written. B is should it be a tensor product? I don't remember. You just check. Because I was very confident, but it's better I check it. That's okay. There is no tensor product. Yeah, I have written it correctly. Why is it? This is just a vector, no? I was actually confused because I saw here, but I'm confused about that now, not here. Here, I think this is okay. This is just A plus K prime, where this is up to modulo min, a modulo D, whatever. It takes the vector to that vector. This is the action on the, this is just the permutation matrix, right? Yeah. The easy return it in the let me. Or let's write it like this. So this is okay. Vk is nothing but K plus K prime K. Okay. Summation K equal to 0 to D. This is okay. Yeah. This is okay. Yeah, this is also same thing, right? Convolution. Yeah. Okay. Then you define W of any, maybe I call it as L or something. L. Okay. W of L K is just the multiplication UL of Vk. So then prove, it's very easy to prove all these things. Prove UL Vk is equal to e power 2 pi I LK by D VK UL. I'm sure this is correct, but you can check, you should check it. Okay. If there is a problem, you change it. Okay. I'm sure it's correct. You will get, so they don't commute, they commute up to a constant. Okay. They commute up to a constant. Okay. Now you can define, I mean, this is for 1 up to L. And you have this W of LK, W of L prime K prime, okay, is equal to, here Vk will come, no? E power minus 2 pi I K L prime by D W of L plus L prime K plus K. Okay. This is what is called Weyl commutation relation. Okay. Weyl commutation relation. These are called, these operators, this WL, WLK, whatever is called Weyl operators or Weyl-Heisenberg operator. So these are, if you have D equal to 2, these are precisely the Pauli matrices. And using, acting this on the gamma, no, this is D vector. Okay, these are generalization of Pauli matrices. Just remember, we may need it later. Okay. Okay. So the final thing I want to do, is it time? But we started 15 minutes later, no? So we'll go some more time. I will just do one more thing and stop. It will be relevant to all this. Okay. Which is very easy thing. So we will define what is called, we know what is a pure state. We define what is called purification. Okay. Definition. If rho is a state on HA, okay, then a vector chi in HA, HR, tensor HA, okay, is for some HR, Hilbert space HR, is said to be a purification. Purification, that means it becomes a pure state, that's all. Okay. Purification of rho, if you know that if you can take the partial trace with respect to something and you get back a mixed state. Okay. If you take trace R of this chi, okay, you get rho. This is what is called purification. Definition of purification. Okay. You can amplify the state. You can go to amplify something. You get a pure state. If you take the partial trace of that, you get this rho. Okay. This is what is purification. So that on a bigger space, it will be a pure state. Okay. Proposition. Every rho in L of HA, every state rho in L of HA for every state rho and HR with dimension of HR equal to, you call it dr, greater than rank of rho. Okay. Rank of rho. You take any HR, any rho, okay, there exists a purification. Purification is not unique. There is a purification on HR, tensor, H. Okay. That's what you want. You have to get a vector here so that if you take the map, I mean, this Hilbert space satisfies this condition. If dimension is greater than or equal to rank of rho, okay, then you can I mean, then you have a vector here whose you take the corresponding pure state and you take the marginal, you take the trace, partial trace, you will get rho. Okay? Proof. Okay. So you have HR. So HR as dimension greater than rho. Rho will look like this, right? Summation rho k, ek, ek. Okay? Where ek are orthonormal. Need not be a k equal to 1 to r. It will look like spectral theorem. It will look like this. Okay? So now you take fk, some vectors. In HR. There exist such vectors because the dimension is greater than r. Okay, where r is the rank equal to r. R is the rank. Okay, because the dimension is greater than r, there exist some vectors like that. Now you define chi equal to summation. So there I have lambda k. Lambda k's are positive. Square root of lambda k. Ek tensor. Okay, claim that this is the purification. That's all. You take something, some fk, k equal to 1 to r. Okay. Is it clear? Direct? Maybe we will verify. Okay. Now we want to talk about trace r of chi k. Right? That is equal to trace r of summation k, k prime, lambda k. This will become lambda k, of course. Lambda k. And that will become ek, ek prime, ek prime, tensor fk, fk prime. Right? Sorry. I'm sorry. I have to. This should be fk tensor ek. HR comes in the first, no? First one, no? So it should be fk times ek. So this will be fk, fk prime. So this is ek, ek prime. Okay. Now you take the partial trace r on this. Okay. This will have trace again only when k equal to k prime. This will have trace 1. Otherwise it's 0. So if you just take it, this is just going to be summation lambda k, and k and k prime should be equal, summation over k. Then there's just this ek, which is clear. Okay. So this is it as a purification. There is something called canonical purification. Oh my God, I didn't change the camera. Maybe, but there are only 3 views, 4 views or 5 views I saw last time. Maybe somebody is watching. So I will just explain that. So this says that for a state, every row, every state, we have a purification like that. Okay. So we just take, I mean, you can keep in one window this board and then run in the other window whatever I talk, it will be clear. Okay. Yeah, it will be clear. That we have a row, then we take some orthonormal vector in HR, which is possible because the rank is greater than that. Then you take this vector, it's direct verification that is the purification. Okay? So now there is something called canonical purification. I will explain that. Square root of rho. So if rho is in L of HA, ST, then if HA equal to HA, tensor HA, and we have gamma in this. You have gamma. Gamma you have, convention I, tensor I. Okay, I equal to 1 to PA minus 1. Okay. Then define chi equal to 1. Rho is positive, so you can take square root of that, okay, times gamma. This is a pure state, of course. Yeah, I mean, this is a vector, so this will give you a pure state. And if you take the partial trace of that, you should get rho. Okay, so let us check. Partial trace A of first one we are taking of chi. Okay. So I think we have to expand it. So this is going to be summation gamma will get, so summation over ij. Okay. 1/10 square root of rho. So which is just ei tensor square root of rho ej right, tensor square root of rho ei square. Let me see whether I have written it correctly. Okay. So 1 tensor rho, this is just ei tensor ei. So ei tensor square root of rho ei. So ei tensor square root of rho ei, ej tensor square root of rho ej. So I have written it correctly, right? Yeah. You will have a sum here, you will have a sum there. If you take the, I mean, chi is that, right? That is equal to this. So you have the trace A of this. Okay? You want to take it. So if you take the first trace, now what do you want to get? We want to say that, yeah, we take the first trace of that. Then we just get summation over I, rho, square root of rho ei, square root of rho ei. I equal to 1 to 0 to dA minus 1. Is it clear? This is rho. We will verify that. So let xi is in some vector in HA, okay? Then summation I equal to 0 to dA minus 1 of square root of rho ei, square root of rho ei acting on xi, okay? Which we get this vector like that. So which you can write the summation I equal to 0 to dA minus 1 square root of xi. And I want to say that, I mean, I want to say the following. I call this as some sigma, okay? Call this as sigma. Then sigma xi eta, okay, equal to sigma, I will write the other way, sorry. Sigma xi eta, okay. Then that will be eta square root of rho ei, rho square root of rho ei xi, right? Okay. Right, no? So you, because it's positive, you can bring it here. It is just rho square root of rho eta, okay, square root of rho ei xi, which here, I mean, ei, square root of rho ei xi. Okay. I mean, I can take rho ei square root of rho xi because rho is positive, symmetric. I am taking eta sigma xi, where sigma is this. Okay. So I put a xi here and I put a eta here. Okay. Put a eta here. Then I get this. Just calculate this. I get this. So I get something like this, where you have a summation I equal to 0 to dA minus 1. Okay. I mean, I want to show that this is nothing but rho. Okay. So that's what I'm verifying. Okay. Maybe there is a simple way, but this is what I can see now. Okay. So we have this. Now you can take this inside. This is rho sigma ei with ei. This will just give square root of rho psi e. This is just the orthogonal decomposition of that. So this is just square root of, I mean, you take the sum inside. You take the sum inside. You take this and they take the sum inside. Okay, this is just rho eta square root of rho psi. So which is just eta square root of rho. Sorry, square root of rho you take rho psi. Square root of rho you take it here. So which is just rho psi. Okay. So we have this is equal to this. So rho equal to sigma. Whatever. We'll stop here. Hope it's all recorded.